So the recording is now started. There we go. All right. So this is kind of interesting in a way because it really shows you that the labs actually include a lot of information and instructions that you may have neglected for some in some cases. So what I'll do is I am going to a particular question here that I think is going to address the issue, and I will talk about what the issue is to begin with. I think it is this one here. Let me double check. I think that's the one. Nope. I think it is this one. I'm double checking. Nope, it's not that one either. Pretty sure one of the programs has it. This may not be the correct one. It's the one that makes two calls, to the same function, but I cannot remember which lab has it, so I'm gonna have to look for it. Okay, I know it's not this one. Stack operations. I don't think it's this one, but I will double check, see if it's this one. Mm, I don't think it's this one. I don't think it's this particular lab, but I will double check. Uh, I think it's the one that I just showed you a little bit earlier. Nope, it's definitely not this one. All right, let me go back and check for the last time, whether it was the one that I was talking about, which was parameters and return value. All right, one more time. Just check this out. Because I, hmm? Oh, okay. Because I vaguely remember it has to do with a function that returns 5, and then we are calling the function twice in order to add, the return value of the two function calls. But I could be wrong. Yep, it is not this one. It's another one. Okay, fine. I won't be looking for it. But let me first describe what the issue is. The issue is um, you need to add the return value of two different function calls. And because the caller callee agreement says, if you call a function, none of the registers will be preserved. So that means register A, register B, and register C, they are all not preserved, especially in the case of a recursion, because in the case of a recursion, you're calling the same function. So whatever register you are using, the recursive call is going to use exactly the same registers. So that means your return value, which was stored in register A, is going to be gone. Okay. So I think what we can do is so I can change the plan a little bit about what we'll talk about today. So what we'll do is we are going to talk about the program that your homework assignment was about, and then we'll start with that. So we can talk about the solution of that one first. And let me see, where is the homework assignment? This one here. There we go. All right, so this is a Fibonacci, okay? So that's why it's called Fib. And we'll save the zip file, and then we'll take a look at the program. All right. So even if you could not get the program to work, the attempt to get the program to work is really important because you will be running into problems, okay, which is kind of expected, okay, but running into the problem and trying to solve the problem is how you kind of learn all the techniques in this class. So we'll go ahead and just kind of play with that one. Okay, fib.zip. And then we'll take a look at the C code on one side and take a look at the assembly code on the other side as usual. All right, so here's the C code. The main function is already done, and your job is only to implement the Fibonacci program, which only consists of one line in the C code on line 5. Okay, so now we go back here and we'll do things in my typical fashion, which does not mean that you have to do it the same way, but I think there are reasons why I do it in a certain way. So the way I do it is I always, come up with the labels first. And in this case, LVS is defined to be 0, okay, because there are no local variables whatsoever. So that means f underscore n, which is our only parameter, is going to be f underscore LVS 1 plus. And at this point, I'm not going to explain why we have the 1 plus, what that 1 is accounting for, because we have talked about that a few times already. Um, but for people who cannot remember, you can always kind of go back to the previous classes and the notes and find out what that 1 is representing. All right, so we are now going to go for the usual things, even though we have no local variables. I'm still going to reserve, quote unquote, reserve space for the local variables and then also to deallocate, just so that, in case I actually do have local variables, I do not have to change this program to deal with that. Okay, so that's for allocation. And then this is for deallocation. And then right after that, I have the usual return code, which is LDB comma D, increment D, and then JMPB. All right, so in between the allocation and the deallocation of local variables, I can now finally implement the C code on line 5 of the C code. So are we doing okay so far? Okay, so I'm just making a shell of the program first, and that's it. So if you want to check whether the program is working or not, one thing you can do right away is simply to say, okay, this function is just going to return a 0 or whatever value you want to use to check whether main is working or not. Okay, because because main is supposed to store the return value of calling f into the local variable x and call it a day. So that means, by doing this, it should store a 0 into x no matter what parameter you use to pass to the function, but it's a good way to kind of double check everything, especially if you run it through River Spider. You can actually see how things are pushed on the stack, how the stack pointer is adjusted, and all kinds of good stuff like that. So it's always a good kind of verification that the program is working up to this point. But I'm not going to do that because I do have another program that I want to go over today. So I will go straight into the implementation of the code. So the first thing I need to do is to compare n against 2. If it is less than, I want to return just n itself. If it is not, I want to return this whole bunch of stuff here. Okay, so that means I need to get the value of n into a register. That pattern of code has been talked about, I think, for the last 2 classes already. So I'm not going to get into the details of that. So I'll just go like LDI. I can use any register at this point. Register A is fine. It will be F underscore N, add AD, LDAA. So now register A has the value of parameter N. I need to compare this to 2, so that means I need to load the constant of 2 into another register, let's say register B. So at this point, I can compare the value of parameter n against the constant of 2. So now the question is, which way do I want to compare? There are 2 ways to do this. Okay, we have to use the compare instruction. So if you want to do it the way that I normally do things, which is if n is not less than 2, let's go to else. Um, then we want to compare the in the opposite way. Okay, it's not n2, it is going to be 2n, which means ba. So this is basically calculating what is 2 minus n. So if I compare this way, it means if 2 is less than n, I should go to the else case. So now we need a JCI to the else case. So I'm going to say f else 0 because I can consider a ternary expression as a conditional statement, and we are going to the else branch because we are going to the third part of the ternary expression. So that's one way, and then we have to follow up with a JZI because when n is indeed 2, we also want to branch to the else case. Okay, first of all, does that make sense? Okay, so if 2 is less than n, we go to the third part of the ternary expression. If 2 equals to n, we also want to the else case. So that is kind of consistent with the way I describe the conditional statement. Yep, go ahead. LDAA. So LDAA is no different from any load instruction. The It will go to RAM, use register A as the address, grab the content at that location, and then put it into register A itself. So basically, it is a dereference using register A, but after the dereference, we also store the value back into register A. Yeah, so LDAA is much more common than STAA because typically we do not need to store something back into where the register points to. So ST with the same register is kind of rare, but LD with the same register is fairly common, because every time we need to dereference and you don't need the pointer anymore, we just use a LDAA or LDBB or LDCC. All right, so this is the then case, and now we have the else case over here, which also means I need something to go around the else case here. So JMPI, which is unconditional, to end if 0 is going to go around the else case. So I put end if 0 over here. So I set up the structure first. Okay, this is the way I code. Is I set up the structure. I set up the structure of the conditional statement, put in all the labels, the unconditional branch, and then I can go back and backfill what needs to go into those specific branches. So if you want to, kind of make it clear that this is the else branch, then we can also do it that way. Okay. Do we have any questions about the framework of the quote unquote conditional statement? Even though it is not a statement, it is an expression, but it has the same structure as a conditional statement. We good? All right, cool. So the then case actually has nothing to do, okay? If you really insist that you want to put an instruction here, you can put a no up here. Why? Because register A is supposed to store the return value, and it already has the return value, which is n. So that means, the then case really doesn't have anything to do. I have n already in register A, so I don't have to do anything and just go like, okay, skip over the else case, go to the end if, and call it a day. Okay, so that's how the then case is set up. The else case, on the other hand, is a little bit more hairy because it is corresponding to the actual recursive call to f of n minus 1 plus f of n minus 2. Okay, so the way this is done is we'll handle the easy one first, okay, which is, and let's go call f with n minus 1. We know register A has n in it right now, so decrement A is going to get us n minus 1. I am not changing parameter n. I'm simply subtracting 1 from the value of parameter n. Okay, so parameter n is not changed. As a result of this, decrement D, STDA. In other words, we now push n minus 1 on the stack, and we are now ready to call n again. So that means we also have to do LDI, a dot 6 plus, decrement D, STDA. This is our return address. We're pushing the return address on the stack. Now we can do a regular jump to the function that we're calling. Turns out to be f again, okay, which is okay. There's no problem with calling a function from within the function itself, because if we can do that in the C code, we can also do that in the assembly code. When f returns, okay, we will do an increment d in order to deallocate the 1 byte that is used by the argument that is sitting on the stack. So right now on line 42, the return value of f of n minus 1 is now in register A, which is what I need in order to perform the addition. But before I perform the addition, I also have to call f again with n minus 2 as the argument. So that is the problem. It's like, we need to save register A to some place, um, so that we can do the add later on. we cannot just copy that to register B because if this function is going to use register B, for a particular purpose, so will the recursion. Now you can say, but so far we have not used register C. Why don't we save it into register C? Because when you're doing recursion, that recursive call will also use register C for whatever purpose you use register C for in this particular instance. So any register this the implementation of F is going to use, the recursive call will also use that. So go ahead and then back there. Yes. 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 Yep. Yep. You save it on the stack. The stack is the only safe place to save the return value. Yes, go ahead. On line 14. Line 14 does not have anything to do with the return address. You mean the LVS, the dot six plus? That is correct. They're not necessary. I just do it because, this way, if I need to add additional local variables later, I don't have to worry about the structure of the code. That's just me future proofing the code. It doesn't really do anything useful, but it's not wrong either. Okay? Because if you do something that is not necessary, it's easier to kind of take it out later on when you know that you won't need anything else. This function is all done. But on the other hand, if you do not, if you try to optimize before you check to make sure the code is all correct, that means, in the future, you might need to make adjustments that can propagate a lot of changes throughout the code. So I would much rather future proof the code to initially later on to find out that, oh, this is really not necessary, and take those out. Just comment out the code that is not actually needed. All right, so now we need to push register A on the stack, which means we have to decrement D and then stda. That's pushing the return value of f of n minus 1 on the stack so that, when we come back from the second call to f, which is f of n minus 2, we can then pop the return value from the first call and then add the two values together. So for people who go like, okay, but line 41 and line 43, they cancel out each other. That means, we don't need either one. That is correct as well. Okay. But in this case, I want to leave them up here. Okay. Because decrement D and increment D, they are conceptually doing something that are entirely different. One is for deallocating the argument, which is what a function call should do anyway. And then the other one is for pushing the return value on the stack. So even though they do cancel out each other, they both can go away at the same time without changing the correctness of the code. For conceptual purposes, it is good to leave them both in the code just so that you can associate. It's like, okay, a proper function call should always deallocate the argument. A proper push should always decrement the stack pointer. So it is better to kind of leave it like this, just so that you can associate chunks of code, as one single logical block, and not to, have to interpret what is going on here. So at this point, I can no longer assume that register A has n in it because register A actually has the return value of n minus 1. So it's time for me to recompute the value of n. So that means, I have to kind of do the whole thing again. But this time I have to add one more to the offset because we have just pushed something at the bottom or below the base of the frame for this function call. Okay, because that extra push of line 43 and line 44 decrements the stack pointer. So the stack pointer is now pointing to 1 byte below the actual frame of function f itself. Yes. The base case is already done. The base case is line 27, which is just a no op. line 29 is line 29 is corresponding to the entry point of the else, which is the third part of the ternary expression. So that really is the best, it is the correct place for the recursive call. Go ahead. Hmm. But you can ask the same question in the C code. It is not about the assembly language representation, it is about the logic of the code. Because the C code can run into the same problem. But the C code is easier to read, but you can see that every time we do a recursive call, n is decreased by 1 or 2, right? So that means, if n was not less than 2 before, eventually it will be less than 2. And the assembly code is nothing more than just a different way to represent the same logic and the same code, except it is a little bit more tedious. Okay, go ahead. Hmm. So Fn itself is the offset from where the stack from the base of the frame to parameter n. Okay, that's what the label is representing. Unfortunately, the stack pointer used to point to the base of the frame, okay, because the stack pointer points to the last item that you either allocate or push. But now that we push the return value of the first call, the stack pointer is now pointing to 1 byte below the base of the frame. So that means anything, if I need to access anything from the frame, the base is no longer pointed to by the stack pointer. It is 1 byte after where the stack pointer points to. So all the offsets are now off by 1 because of this decrement D, because of the decrement D on line 43. Okay, so so I know this program can be a little bit difficult, but after you try to do it yourself and you go like, okay, I couldn't get it to work, and now you read the solution, it clicks a lot better compared to people who did not give it an attempt. So it is really important to at least give it an attempt as much as possible, before you go like, okay, I can only get it up to this far. Okay, because the point value of the assignment is not that significant. Okay, it is what you learn in the process of trying to do the homework that is important, because that also primes your mind so that when I talk about the solution, it goes like, okay, I know exactly what that is doing and how this is solving the problem that I was having some problem with. So that's kind of the importance of the homework assignment. Okay, so now we have another LDAA. Okay, so once again, register A had the address of n. Now we have the value of n, but this time we need to decrement it twice because the second call is trying to push n minus 2 on the stack, and this is just n. Oh, decrement A, not D. There we go. So now we are ready to push that on the stack. So that's the decrement D, STDA. So now we're pushing n minus 2 on the stack. And then we now have to push the return address, which is LDI. I can reuse register A, okay, dot 6 plus, decrement D, STDA again. JMPI to F, which is the function that we are calling, turns out to be the same function that we are in, but that doesn't change the caller-callee agreement. Even when the caller and the callee are the same function, it doesn't change the agreement or how it's supposed to work. So after this, we have to increment D to get rid of n minus 2, which is sitting on the stack. Now is the magic. Okay, this is the magical part, which is I have register A storing the return value of n f of n minus 2. That's in register A right now. But the return value of f of n minus 1 is sitting on the stack, where the stack pointer is pointing to it right now. So now all I need to do is to pop that value into a register other than register A, and then we can just add those two. So now we have to pop. So popping, if you remember, is to LD into a register, and then you increment the stack pointer. So this is popping the return value of f of n minus 1 into, in this case, register B. And now I just have to add register B to register A. That becomes the actual result of what I need on the third part of the ternary expression, and we are done. So are we doing okay so far with understanding what the code is doing? Yes, go ahead. Sure. Let me scroll up first. Mm-hmm. Mm-hmm. Nope. Nope. According to the caller-callee agreement, the return address is popped by the callee. So the only thing that is still sitting on the stack is the argument itself. After which line? So after the increment of line 41, the stack pointer will once again point to the base of the frame, which is the return address. No, it's just the return address. It is just the return address because we can, looking at this code, we do not know whether we're dealing with the first call or the second call or the third call because the code of the function stays exactly the same. The only difference is where's the stack pointer pointing to. The frames are unique with each invocation, but the code is the same. Yep. Mm-hmm. On which line? Don't think we have an LD into register D because that would destroy the stack pointer, and that's probably not a good idea. Is that from the first call to F or the second recursive call to F? The second recursive to call the second recursive call to F is here. So we push. So line 46 is the first line of the second call of the recursive call, and it ended up at um, line 63, sorry. So from 46 to 63 is the second call. That's the recursive call. The increment D, you mean this increment D on line 62? So that increment D is for deallocating the argument that is still sitting on the stack, which is n minus 2. Because it's the caller's responsibility to deallocate all the arguments. So the return from the callee is coming back to line 62. So the caller goes like, okay, I know the function is all done. The return value is in register A, but the argument that I pushed earlier on the stack, which is n minus 2, is still sitting on the stack. There's no need for that n minus 2 to be sitting on the stack right now because the function call is concluded. So that means, okay, as the caller, I know that, this byte is not needed. Let's deallocate it. That's what line 62 is doing. And then line 65, that increment D is for popping the return value of f of n minus 1 because, we also do not need that anymore now that we have retrieved. So now that we have retrieved that particular value into register B, we don't need it on the stack anymore because we're going to do something with it, in the following part of the code. Yes. So scroll up like this. Uh-huh. Here. Oh, okay. So you want to show the as much as possible for the else. Uh-huh. That's that's the most I can do without losing. So I would say that this program, I would share this with you, um, but this would be a good program to document, to comment and analyze and document. You can also run it, okay? In fact, I'm going to run it, okay? So I want to show you what it looks like and whether it is correct or not, because it is entirely possible, I hope, that I actually made a mistake and this doesn't do what it claims to do. Because then I can also show you how to debug a program that is written in assembly. So do we have any questions about the source code? Because, yeah, go ahead. Line 41 is part of the call. So line 41 is part of the call in order to get rid of the argument that we pushed here. Because we pushed um, n minus 1 on line 33. So that is still sitting on the stack by the time we get to line 41. But that argument still sitting on the stack has no purpose now because the function is done already. So that's why we increment d to deallocate the argument that was still sitting on the stack. Yeah, it's not exactly a pop because I'm not retrieving that into another register. I simply said, this location on the stack is no longer of any use to me. So I want to be able to reuse that location. Line 43 is for pushing the return value of f of n minus 1 on the stack because the stack is the only safe place that I can save the return value because none of the registers is saved to save 2 because the recursive call is going to use exactly the same registers. So are we good? All right. All right. So any other questions before I actually run this code and then we can actually look at the stack and see how the stack is being used. Yes. Yeah. What do you mean by temporary? You mean the return value of f of n minus 1? Can we store that to, well, guess what? Guess where local variables are located? So, okay, so I like that idea because what you are basically suggesting is to change the way we express the code. So basically what you're suggesting is we break it up. Okay, so I'm going to use F1 to represent the new logic here. So uint 8 underscore t and okay. So in this case, we explicitly use a local variable. Okay, so we say uint 8 underscore t. We'll just say well, I'll just call it X, okay? So in this case, we are basically using a conditional statement, okay? So we go like this, so, and then we return, okay, I'm gonna do the bad programming practice and just say, this is gonna return n right here. And now this one is gonna I'll break this line into two different parts. The first part is simply saying x equals to f of n minus 1. The second part says, return x plus f of n minus 2. So and also change this to f1 and this one also to f1. Okay, first of all, does everybody see that the second implementation or the second C function f1 is basically the same as the original f? Okay, first of all, do we see that? Okay, f1 as a function is the same as function f in terms of what it returns, what it computes. Okay, but it has an explicit local variable x to store the return value of f of n minus 1, then later on retrieve that and add it to the return value of f of n minus 2. Is that okay? So we don't need this trick here if I were to implement F1 because the extra byte to store the return value of f of n minus 1 is now explicit as a local variable. But guess what? In the end, it's doing exactly the same thing because where do we put local variables? On the stack. Exactly. So the only difference between F and F1 is F1 makes that extra byte explicit, and F is just implicitly using one extra location on the stack when we need it. Is that okay? So I think that's a really good question because it prompts me to explain the same concept but using an extra local variable to basically do the same thing as the location that we used earlier to store the return value of f of n minus 1. All right. Okay. So excellent. So we are not implementing F1, okay? So we are just implementing F. So now we are ready to test run the code. Are there any other questions you guys want me to answer? Yes, please. Nope. It is part of the agreement. Okay. Can you point to the line number that you're line 17? Nope, that has nothing to do with it. This one is just using register A to help me compute eventually the value of n. So that has nothing to do with why we can assume the return value to be in register A. That is simply a caller callee agreement that a function always returns a scalar value in register A. It is about how we use the register and what can be assumed between the caller and the callee. Yes. Mm-hmm. Yes, because A is the register for the return value. No, we're returning A because add AB stores the sum in A, not in B. Okay, so you're looking at, so this computes the sum and it stores it in register A. And then after that, we do not mess around with register A because register A needs to be preserved after line 67 because on line 67, we compute the actual return value. And then from that point on, I cannot use register A for anything else because your register A is now serving a particular purpose, which is to uh, communicate the return value back to the caller. And that's why I have to use anything but register A or register D on lines 71 to 75. So I could have used register C, could have used register B, or a mixture of the two, but I cannot use register A because register A at that point is already specifying the return value, and I cannot override it. Uh, okay. All right. So what we'll do is this program may look really difficult to understand, um, but the best way to really understand what is going on, how the stack is being used, how the logic works, what registers containing what, is to run it. Okay, that really is the best way to understand what this program is doing. So we'll go ahead and change the program a little bit, and we'll just say that we want to figure out what is f of 2. Okay, because f of 2 is the smallest value that will make it go recursive. Okay, and yet it does not go too far so that the trace is still more easily understood. Okay, So that's what we're going to do. And we'll also, change that in the C code if we want to run the C code also, because, this is basically your assembly code should behave the same way as the C code in terms of what it computes. All right, so we are saving both of those, and we'll go ahead and run the C code first. Okay, so we'll do a gcc-g-o f.c. Oh, it's fib. There we go. Okay, gdb fib. And then we put a breakpoint on line 23, run the code, print the value of x. It is 1. Okay, so now we go to try to test out the assembly code. So we now go to my document CISP310 with a spider, and then we just run fib.ttp-asm. All right, and now we can go back to the assembler. There we go. All right. So the first thing is, what are we supposed to see in this code? And we're gonna wait. Array result was not expanded because it would overwrite data in G96. So that's my bad because I put something there. Not G96 is right here. So I just have to remove that. Okay. All right. So how do we understand what is going on here? This program is a little bit harder to understand because we are reusing stack space. Okay, so it's not a one-way street and it just go back in a linear fashion. It goes back and forth. Okay, and that means you really have to go line by line when you look at the trace. All right, so let me go back to the uh, editor. I cannot remember where did I stash it. Here, there we go. So now we want to kind of draw a picture of how the stack space is being used. Location FF is still used by the return address from main back to the entry code. So that part has not changed. Okay, so that's a fairly typical thing that we do. Location FE is variable x of main, okay, because that takes up a byte. And then location FD um, is also only serving one particular purpose. It is only serving the purpose of the parameter or the argument. Sorry, it's serving as the argument on line 22 of the C code, which is a simple 2. Location FC is serving also a single purpose, which is the return address from F to main. Now, below this is a little bit trickier because FB as a location would first be used to pass the argument of 1 to the recursive call, and then location FA will first be used as the return address from F back to F. So that's the first use of these two locations. Then after this, location FB will store F of 1, okay? And then we are going to reuse FA to pass a 0 to function f again. So that means f9 will then be used to also store the return address from f to f. So according to this, this should be the extent of how much space we're going to use on the stack. Um, but the difficult part is below FB or FB and below, those locations, two of those locations are repurposed. So that means you cannot just look at the trace once and say, oh, okay, this is what we store at that location, because they're going to be used twice, during the execution of this program. So are we good so far in terms of analyzing how the stack is going to be used? Okay, so now the next thing we can do is to actually look at the trace and find out what it looks like. So we can now go back to the trace, which is here. And we start at the beginning. And this time we can just kind of focus on RAM write operations. And as expected, location FF is the return address from main back to the entry point, which according to the structure of the entry point code is always location 9. That's always where main wants to go back to. So I think some of you might remember it's like, oh, how come it is always 09 that we store into location FF? And that has to do with the entry code stays pretty much exactly the same across all the sample programs. So now we go down a little bit and then we go like, okay, why is FE not getting a value? Because location FE is local variable X, which means we just reserve the location until we store something to a local variable. We're just going like, okay, we are saving this location for local variable X of main, but I have nothing to store right now. And that's why we don't see any store operation to location FE. Location FD is the two of the first call to F, okay? Because in the main we say, okay, give me F of 2, okay? And that's what the 2 is. It is the argument of F of 2. And then we move down a little bit. This is the return address back to main, okay? And we can double check all of this too. We can go to the assemble tab and go to the location that we were looking at, which is 42. And then we can ask, is it 42? I don't think it's 42. 4C, okay, so it is location F4C. And now we can go to location 4C in the assembler. And then we ask, is that where we want the function to return to? The answer is yes. Okay, how do we know? Because unless we are returning to this location, there is no way we are going to execute this instruction when it is right after a unconditional branch. Does everybody understand that argument, what I was just talking about? Any instruction that is right after a JMPI instruction would have no chance of execution unless there's some way to go back to that location. Okay, and returning from a function is doing exactly that. Okay, so that means location 4C is indeed the correct location to return to in main after the initial call to F. So we good? Yep, go ahead. Eventually, yes. So Fibonacci is a little bit funky because it goes back and forth. So if you have like f of let's see, so 0, 1, 2, and 3. So if you try f of 3, then it would have there would be 4 invocations altogether, and the last one is going to be nested. So the way it uses the stack is going to be call, 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 return, and then call again, and then return, return, and then call, and then call, call. So it's going to be because it will reuse locations in that case. So it's not going to be very easy to actually visualize how it is using the stack. F of 2 is easier because we're only reusing like 2 locations, and it will be kind of clear how those locations are getting reused. Okay. All right. So getting back to the trays. So now we go to the recursive call, right? So the recursive call is going to be, it will stop the recursion because now we have f of 1. Oh, wait, I take it back. This is still f of 2. Um, so then it will call f of 1, and f of 1 is here. Location fb is the argument of f of 1. And then we have 2, 4 as the location to return to. So now we're going to double check again. Okay, where is location 2, 4? Location 2, 4 is right here. It is right after the first recursive call to F. So it is a valid return address. It is the return address right after the first recursive call in function F. So that's how things are being pushed on the stack. And it is also important. It's easy. It's easier if you're doing this on your own computer because my screen only has so much resolution, and you guys can only have so good of an eyesight. So I cannot really open up multiple windows so I can see multiple things at the same time. But when you're home, kind of tracking all this down, you can open up the analyzer on one screen, on in one window, look at this in another window, and yet open up another one for taking notes, because that's how you kind of link everything together. So now we have just explained, where this one is coming from and how this FA, where this is coming from. So now we continue, and we are going to see the value of f of 1, which is going to be, what is the value of f of 1? No, the value of f of 1 is 1, because 1 is less than 2. We simply return the 1. Okay, so we will see the 1, which is what this is representing, being stored again at location fb. Okay, now in this case, it just so happens that the argument is the same as the return value. Okay, it is not generally going to be the same, but in this case they are indeed the same. So if we switch back to the trace, okay, go to the analysis tab here, we would see location FB to store a 0, 1 again, but that 0, 1 is not an argument. It is the return value from the first call to function. This is the result of the first recursive call. Is that okay? So I'm trying to kind of illustrate what we see in the trace with what we expected to see on the stack, just based on the earlier exercise. And then to you, what is also important is the actual code that executes in between, because this is more or less just my verification of whether the program is working or not. But how it worked out this way, what is the logic, who is calling who, and how do we make a decision whether to make a call or not to make a call, that is in the actual code, which is basically what column F and G are about. So now, so after this, we are going to use location FA to store 0, okay, because that's n minus 2. So go, go, go right here, okay, and then location F9 is going to store the return address of the second recursive call in the function, which is supposed to be 3.5. So now we go to the assemble tab, go to location 3.5, and make sure that we are pushing correctly the return address of the second recursive call, and it really is the correct location, because you can see how the increment D, which is at location 3.5, is right after a JMPI, and this is the second recursive call in the function. Okay, so right now, okay, if we are to go back to this kind of conceptual diagram, it matches, everything is matching up. Yep. So that would be, um, okay, so the way we can find that in the trace is when we use the return address to main. Okay, so that would be a clue of how we can find out. So now so to answer your question, let me go. Does everybody understand what the question was? The question was, how do we know that register A returns the correct value back to main? Is that correct? It is simply putting a value in register A. In other words, in the code here, line 67 specifies the return value for the recursive case, and then line okay, so line 27 is kind of the non-recursive case, because for the non-recursive case, we put the value of n into register A on line 19 already. So there's no need for me to, let's recompute the value of n and put it into register A, because the value of n is already in register A by the time we get to line 27. So is that what you're asking? Okay, gotcha. Yep. All right. So now the biggest question is, did we get everything done correctly? Do we store 1 into local variable x of main? So that becomes the kind of the final question. So that would be location FE. So let's go back to the analysis tab. And then we just skip a whole bunch of stuff until we get to the store to location FE, which we just saw earlier right here. So this is storing f of 2 to x in main, and it is the correct value, okay, because f of 2 is indeed 1. Is that okay? All right. So if you are on the computer right now, you can go to the assembler sheet right now and just make a copy. So this way, you don't have to rerun this program on your own, in order to take a snapshot of it. And then you can just start to comment, what you see, in the trace, what is it doing, and so on. You can start to annotate the entire trace. So I'm going to leave this one up, because I need to talk about structures next. But I will try to answer every question there is about this program before we move on to structures. Yes. No, not when you have f of 3. Because, okay, so let's think about f of 3. F of 3, because 3 is not less than 2, so f of 3 is f of 2 plus f of 1, right? But we already know f of 2 is 1, f of 1 is also 1, so that means f of 3 is 2. Yep. hmm But the trace is going to be significantly longer than this because because of the way the recursive call is structured. So the trace of f of 3 is approximately twice as long as f of 2 because it's exponential. The length of the trace is exponential to n. All right. So do we have any questions about the techniques that I was using today? Okay. So the only trick really was, oh, okay, the return value, we have no place to stash it. Let's save it on the stack. What are you referring to? What is going on the stack? No, it's the value goes back to main because of register A is the agreed upon register to return a value. Yep. Okay. So very good. Um, so this may also be a good time to kind of revisit something that we have announced earlier, like I think 2 classes ago. I cannot remember when. Um, and that is the Chat GPT tutor. Because what you can do with the tutor is, okay, well, so I'm going to illustrate what you can do. I know many professors say do not use your Chat GPT and do not try to use Chat GPT to do your homework, but you're using this, to kind of help out in your understanding of the material. So now you can say, can you help me implement the following program? Okay, and then we'll just go ahead and do a backtake 3 times. See, ChatGPT actually understands Markdown, so this way you are helping ChatGPT to identify which section is the code and which section is really just text. So now we can go back to the homework assignment, which is here, and then we can copy the C code. Okay, so go back to here, xclip dash cell clip redirect fib.c. So now the C program is in the clipboard. Control V, back, tick, tick, tick. There we go. Huh? Well, it won't give you the actual code, but it would explain certain things and, um, like, where things are on the stack, blah, 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 and look at this. This is exactly what I had. Shocking. It's almost like your tech just cloned his mind, using ChatGPT. It is not supposed to give you actual instructions. That's what I told it not to do. So if it gave you instructions, it is already against what I told it to do or told it not to do. Yeah. So well, it obviously it's not perfect, because if ChatGPT is capable of giving you like the perfect answer, I can retire. Right now, right now, if I were to retire right now, the department won't be happy about it because nobody is planning to pick up this class. I will already try my best to pass it on to my colleagues, especially the younger ones, because they'll be around for a lot longer, and none of them wants to teach this class. It's because of you guys. I blame it on you. Hmm? When are you going to write assembly code? Okay, so I can answer that question. Um, all right. So I will point out some devices, where you go like, okay, what are these things? So some of these is called a AT Tiny, and we can go check out the prices of such a chip. Okay, so we can go to DigiKey. This is my go-to place for um. Oh, that's a 85, not a 95. Okay, there we go. So it's a microcontroller. Okay, so we go to microcontrollers. And then we don't have to go any further. It's already kind of giving you an idea of how much these cost. So if you buy one, it is $1.50. If you are to buy 2,000 at a time, it is $1.31. And some of these chips are even less expensive than that. They are sub-dollar. So sub-dollar, less than a dollar. Yeah, so they're less than the dollar each, okay? And you're only ordering at quantities of 2,000, which is not a whole lot, okay? Because when you, so let's just say somebody wants to revive the Furby, okay? If you don't know what a Furby is, you can go online and search for it. So let's just say that somebody wants to wants to revive the Furby as a toy, okay? And you'll be selling, huh? Well, because we can make them even more creepy. Okay. In my CISP 440 class, one of the questions was, okay, tech was trying to dominate the world, okay, as in brain, Pinky and the Brain. And the way to do it is to, sneak tech GPT and get it installed onto the Furbies. Anyway, uh, so you want to put a processor on a toy that you think will sell millions. Okay, so when you order these parts, you're not going to order like 10 or 20. You're not going to order 200, 2,000 at a time. You'll be ordering like 10,000, 100,000 at a time. So that means the price goes way down. Okay, I'm not sure whether it has ways of specifying huge quantities here because the largest quantity is only 2,000, 6,000. There we go. So with this one, the regular price is $2 each, and then if you order 6,000 at a time, it's $1.66. Anyway, the whole point is there are MCUs, okay, microcontroller units that you can get for not a whole lot of money. Yes, go ahead. Yeah, yeah. So if you buy 50, then you'll be using the same price for each. So with this one, if they have it in stock, you'll be paying $2 each. So for 50, if you order 50, it'll be $100. Yep. And these are interesting chips because they are um, all you need is just power. Okay, get a 1.5 volt, AA battery, and you can power up these things for days, if not longer. But the problem is, how much RAM does it have? Well, how do you program these things? So you click on one of these, okay? Click on one of these, and then you go to it's obsolete. That's okay. We're just going to check out the data sheet. So this is the data sheet, which is the quote unquote the specification of a chip like this, and they come with one, depending on the version, they come with 128, 256, or 512 bytes of RAM that is internal to the chip. It is on chip. So that makes my processor look like a dinosaur. Okay, because hey, you can get twice the amount of RAM on these things, and the best part is the program is not in RAM. The program is in flash. So all the RAM, you can use all of those for the stack because the program itself is somewhere else. The program actually has a pretty large space. You have 2, 4, or 8 kilobytes of locations, or yeah, so you have up to 8 kilobytes of space to store just the program. That space is not shared with the stack or your global variables. Okay, you can write very, by our standard, very complex programs using this kind of chip. But the problem is there's no compiler can really target this kind of processor because most compilers assume a certain amount of RAM, for the stack and all the other stuff. So they cannot really target chips that do not have the necessary resources. So that means, in order to make use of these chips, what are you going to do? Exactly. Huh? It is for, well, these are called microcontrollers, but this branch of software development is called embedded system development, which is kind of a niche area. And niche is good in the era of AI because there are not as many training material to talk about embedded system programming or the concepts thereof. Okay, a lot of concerns that are valid in embedded system programming do not are non-issues for regular programming. So that means I think the ability of AI to write code is way behind when it comes to this kind of niche programming compared to your daily, usual kind of programming. So, say again? Huh? Web development. Oh, oh yeah. Web development is pretty much dead. There's no need for people to do it anymore. Yep. Or any one of the other LLMs. Yeah, some people say that Claude is the best for coding. Not Yep. But this kind of programming still is too difficult for AI, because there are a lot of concerns. It's mostly because it is not that well documented. It's kind of more of a trade skill. No university that I know of actually teach embedded system programming. So you can get your general computer science degree, but then everything that is actual embedded system programming, you kind of have to learn it, on the job. And that, as a result, you don't have textbooks and a lot of training material for AI to train AIs on this. Yep, not entirely. Okay, it depends on what you're doing. Um, I have no CE degree. I don't have any computer engineering degree, but I worked as an embedded system developer, for a long time, and you can just pick that stuff up. I mean, it's not a big deal. I mean, computer science can easily transition into computer engineering, not so much into double E. Double E can also transition to computer engineering. So it's kind of like a weird overlap between computer science and electrical engineering. Um, but in a very interesting sense, we actually need people like that, because who designed the NVIDIA AI chips? Computer engineers. Yep, yep. Yep. So that's an interesting alternative to computer science The other thing that is also interesting, just in case anyone here is interested in computer engineering, is a lot of UCs and CSU would tag computer engineering, but they would not tag computer science. Why is that? Because computer science is still perceived to be in super high demand. So the UCs and the CSUs goes like, hey, I don't want to make a promise uh, to have you as as a transfer student because I might get someone better than you just based on competition. So that's the idea behind not tagging. Tagging basically means, okay, I can see that you have a 3.3 GPA, and we are really running short on people in this program. We need enough people to start our classes. So how about this? I promise that if you maintain your GPA of 3.3, you are guaranteed a spot at our school because they want to get people as early as possible, right? Okay, I know we are running out of time. Yeah, I did not get to talk about structures. The lab itself is self-contained. It does contain, the necessary concepts. So let's do it anyway, okay? Because most of the lab really is self-contained. Maybe a little part of it is not as self-contained. So we'll go ahead and do it, and if it's really bad, then I will probably just not count this lab, okay? Because this really helps to prepare this class for Thursday too. So we are just kind of reversing a little bit of instruction versus lab. All right, so you still need to know the access code to the lab. Let me give that to you, and then we will go over there. So the lab tonight is called Basic Structures. Unhide it. And the access code is, oh, okay, not very fun or inventive this time.